Hello and welcome to today's webcast, Building Your Water Quality Surveillance and Response System, sponsored by Census Asylum Brand. My name is Alana Maya. I'm the editor for WaterWorld magazine, and I'll be your moderator today. A few housekeeping items before we begin. The slides and audio for today's presentation will be pushed to your screen automatically. If you're running pop-up blocking software, we recommend that you disable it to view this webcast, and we also recommend that you close down any other applications for better performance. You can customize your layout. You can move, resize, or collapse most of the items on your screen so that you can see what's most important to you. If you need to refresh or reset your presentation window, you can press F5 or Command R on a Mac. And for technical difficulties, the help icon in the engagement toolbar provides answers to most of the common questions that people may have. But if you still need assistance, please submit your question through the purple Q&A icon, and a member of our webcast support team will work with you to correct the problem. The Q&A icon is also how you would submit questions for our presenters, and we will discuss those questions during the Q&A portion at the end of the program. Certificate of attendance will be issued automatically via email within 24 hours, and you may also download it by clicking on the yellow certificate icon in the engagement toolbar. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archives, and it will also be accessible for 6 months at waterworld.com. We have a terrific presenter for you today. Zachary Barkjohn is a business development engineer for Census Asylum Brand, working with distributed monitoring technologies and analytics to help utilities improve the performance and reliability of their water distribution systems. He holds a bachelor's and master's degree in civil engineering from North Carolina State and the University of Illinois, respectively. And now, without further ado, I will turn the program over to Zach. Take it away.
Thanks, Alana. And thank you all for joining us today. I'm really excited to tell you all a little bit more about water quality surveillance and response systems. And I want to be really upfront with you that this is not an idea that I had. This is the culmination of a lot of work at the EPA and other agencies. But I thought it was a really pertinent conversation to have and something that I hope you get some benefit from. With that, let's jump in. So the way I see it, there are two critical missions of water utilities: delivering enough flow and pressure for fire suppression, and then on the flip side, delivering clean, high-quality water for sustaining human health. And given that these are the two most critical missions of water utilities, I really see water utilities as protectors of public health. And I actually want to call them agents of public health for this webinar because I actually see a lot of parallels between water quality professionals or just water professionals in general and secret agents or the spies we see in the movies. And if you think about it, I think that translates well because secret agents and spies are obviously a lot of times doing things in the shadows that the public isn't very well aware of what they're doing. But they're trying to keep their community safe. They're trying to keep their country safe. We as water professionals, we're trying to keep the public safe, our community safe. And the public generally doesn't have any idea what we're doing. And just like secret agents who might be fighting people in the shadows or people they can't see, a lot of times our opponents are invisible as well, or at least microscopic, so we can't see them. And what I've got on the screen here is a picture of Jon Snow, and I really consider him one of the first agents of public health. And the reason why I consider him an agent of public health is in the early 1800s, London and England, a lot of the world actually was having issues with cholera outbreaks. And the leading theory was that something called night air was making people sick. But Jon Snow, he was actually a doctor by training, and he looked at the data. And so he started plotting cholera ailments on a map and started to realize that most of the cases were centered around the well. And so that led him to the conclusion that there was something in the water that was making people sick. And so this was a big advancement in the understanding. And really this became the birth of epidemiology and in some senses water quality as well. Fast forward a few hundred years to our current age, and global access to safe drinking water is still a human health risk factor. So what I'm showing here is an article from the Lancet, which is a very esteemed medical journal from 2015. And so the figure at top is showing the leading health risks or the leading factors impacting public health in the year 2000 versus the year 2013. And so what we see in the year 2000 is that unsafe water represented the number 4 most prevalent risk factor affecting public health. The good news is that in 2013, that fell down to number 8. So this is good news globally, but I also want to point out here that this is a global definition of public health, and their minimum exposure level was households having access to water from a pipe supply that is also boiled or filtered, essentially treatment. And so most of us water professionals here in the US or Canada, or if you're a utility professional on this call, you already meet that level of supply, but we know that just having treatment and distribution does not necessarily mean the water is always safe. So I bring this up for 2 reasons. The first is that, this is something to be proud of. In the US, we have come a really long way. Unsafe water is not a huge detriment to human health anymore, but there's further we can go. And it's something we don't really think about all the time. I was talking with the chief information officer at a utility a few weeks ago, and he was saying that he was on a trip up to the North Carolina mountains doing some tubing and got flipped out of his tube and accidentally inhaled a bunch of water and was really sick for a couple of days just because of what was in that mountain stream. And so I just see this as a reminder to us that the work we do is important, and if we let up for an instant, public health can suffer. So traditionally, water quality efforts are focused at the treatment plant. This is where we have the most control over it. If we're going to relate this to secret agents and spy movies, this is headquarters. Henry Darcy was another one of those first agents of water quality or public health, and he started looking at sand filtration and using sand filtration before going into a distribution network to deliver safer, clean water to the residents in France. And that was around the time that people started realizing it's not just the stuff we can see, it's also stuff we can't see. It's things like heavy metals, bacteria and viruses, and things we're finding more about every day, like those endocrine disruptors, personal care products, all those sorts of things. But what I want to focus on here is that when we're at the treatment plant, we are only focused on treating what's in the source water. But we know that water quality can degrade in the distribution system. Distribution systems are huge assets. A lot of times if you look at municipal budgets or the amount of liabilities they have, the infrastructure, especially in the distribution system, is a really big component of that. But it doesn't necessarily get all the attention that the things that people can see do. And so when we're talking about the distribution-dependent contaminants, we're talking about things like bacteria and viruses. And those are things that are impacted by how much chlorine residual or disinfectant residual is left in the distribution system. But as we know, chlorine residual decays over time, and that is a function of what we call water age. And then there's also the impact of leaks and siphons. So I was talking to another utility recently where the general manager was talking about, it's important to him that they really keep their non-revenue water at a minimum, because if they have leaks and they have these siphons, that's an issue for water quality as well. So he was making that connection. It's a rural utility that he runs, And he was saying that, if there's a siphon, there's a good chance that pipe's running through a cow field. And so some of that cow patty is going to end up in the distribution system, which is obviously a health concern. Currently, the mode that we monitor our distribution systems is regulated by grab samples. That's the primary way we go out and we collect samples in the distribution system to ensure that we've got high quality water. And so depending on the size system, there's a lot of variance, but monthly grab samples is pretty common. And a lot of this goes down to the total chloroform rule. But there's another concern we have when we're talking about water quality in the distribution system, and that's the concern over malicious attacks. Although it's really not a high likelihood, if there was an attack on a water system, it could really be catastrophic. So I would like to take a pause right now before we get really into the meat of this presentation and ask you all to fill out a quick survey. And so this goes, how familiar are you with the EPA Surveillance and Response Systems Framework? And I'll give you all a few seconds to answer that. All right, so not sure if everyone got a chance to respond, but it looks like we've got a pretty even response between not at all familiar and somewhat familiar. So it sounds like we're going to have a good discussion today. Before I go on too much further, I will say that on the EPA's website, there's a lot more information than I'll be able to cover today. So if you feel like there's a lot of information you're missing, that's a good place to start. And I'll have that link at the end of the webinar. So getting back to water quality and the issues we have maintaining water quality in the distribution system. In the early 2000s, EPA, as well as some of the other agencies, realized that there was a big gap, especially when it came to malicious attack in our water systems of the United States. And so they started working with utilities to figure out what are the best practices to move forward, what are the best tools in order to protect our water systems from a malicious attack. And so what they did is they came up with this framework, and I want to be very clear, this is a framework, not a regulation. And what they found with these frameworks is that these systems are really effective, not just from protecting against malicious attack, but from the cow patties and the every other issues that we're trying to fight when we're talking about water quality. And so regardless of the actor, whether or not that's the bald guy with the white cat or the microscopic organism, these are some really great tools for protecting water quality. So for the rest of this presentation, I'm essentially going to step through the different components at a high level and give you some of that information, which I hope you'll be able to use to then dive in more into the components that are meaningful to you. There are 5 key data sources that the EPA recommends monitoring, and those include online water quality monitoring. So these are devices actually out in the distribution system monitoring water quality parameters. Enhanced security, so taking another look at what kind of security we have around our remote assets, like our pump stations and tanks, anywhere that somebody can gain access to the system. Metering, tampering, and backflow alarms. And so this is actually utilizing some more advanced technology around the advent of advanced metering infrastructure, or AMI, and leveraging those capabilities. And then on the softer side, customer complaints. So really utilizing our customer base to provide information back to us to understand if there is a problem. And then kind of similarly more on a metaphysical level, the public health surveillance. So tying in with our local public health agencies and getting information from them if there's a possible water contamination event. And so I'll get into each one of these in a little bit more detail. But the first thing the EPA identifies is that these are the possible data sources that can be useful. And the first step is to start paying attention to the ones that you already have. And with that, you need a monitoring program. And so you need a decision tree or some sort of algorithm to tell you, is there a problem or is there not? And although I just have one arrow coming from the monitoring, I want to be clear, this can be done at individual level, or it can be all tied together. It doesn't have to be all one monolithic program. But essentially, we want to be regularly reviewing this data from these different monitoring sources and asking ourselves, is there a problem? If the answer is no, then we just continue on with our business. And this is good news, and this tells us, hey, we're doing a good job. No action needed. But if the answer is yes, that's when we need to have a plan. And so the EPA does a really good job of breaking down what those plans can look like. But in a nutshell, it looks like an iterative process between two events. So there's the consequence management and the sampling and analysis. And what that means is that we're going to try to do whatever we can to minimize the effects of that contamination event, and using sampling and analysis to back up those results to make sure we've got it quarantined where we think it is, and ensure that when we have it all cleaned up, or when we think we have it all cleaned up, it actually is. And so, of course, if you look at this more broadly, the term surveillance and response systems comes from this idea that we've got the surveillance system on the left of we're going to be monitoring these parameters or these different data streams. We're going to be asking ourselves through either automation or people in the loop, is there a problem? And then if there's a problem or a possible problem, that triggers the response phase, and that looks at consequence management and sampling and analysis. Jumping into online water quality monitoring, and what I said before about online water quality monitoring, these are really devices out in the distribution system that are regularly collecting and transmitting data. So you can kind of, when I say monitoring, we're talking about online monitors. We're not necessarily talking about grab sampling. Grab sampling does play an important component, but that's not really included in this framework because it's not very, very continuous. So when we're thinking about online water quality monitors, we're thinking about a couple different things. And the way I like to look at it is, first we need to think about what parameters are valuable. And highest on the list for me, and this is probably going to vary a little utility to utility, but chlorine residual is really important. This isn't necessarily going to stave off malicious attacks, but this is going to tell us when we've got issues in our network that are impacting maybe our water age, or we're overdosing or underdosing. Maybe we've got to break, those sorts of things. So chlorine residual is a good one. pH, this is particularly good if you have a high corrosion potential. Maybe you've got lead or copper service lines. pH may become even more important. But this can also tell us if there's a malicious attack. If we see a big jump in that pH, it can tell us something's happening in the water system. Conductivity is another good one. This is particularly useful if you've got multiple sources of water, maybe a surface water supply and a groundwater supply, because oftentimes the conductivity from those different sources will be different. So this can give us an idea of the mixing of those water supplies. And on the other side of that, it can also help identify malicious attacks if there was a high enough dose. Temperature is an interesting one because even though this isn't really a water quality parameter in itself, it impacts the reactions, impacts chemical reactions. And then some other ones on here, nitrates or nitrites. This could be important if chloramines are being used for secondary disinfection and you're worried about nitrification. And then I've got pressure and flow on there as well for a large, for very much the same reason that you have to understand the hydraulics in order to mitigate water quality issues. The next thing you need to consider is site location, so where you would put an online water quality monitoring station. And so some of the places the EPA recommends are at entry points, at pump stations, at tanks. So these make a lot of sense. One, because that's where the water quality could be changing a good bit. But it also are places a lot of times where you already have the infrastructure needed, which goes into the third piece, which is considerations. But before I would go on there, I do also want to mention service connections are a very good place to consider, especially when those service connections are your own utility infrastructure or infrastructure or buildings that you can friendly access all the time. So like fire stations or municipal buildings, those things. And then of course, we're looking at known problem areas and mixing zones as well, because if you know you've got a problem going on, you may want higher resolution data, say 5-minute data, rather than monthly grab samples in order to really diagnose what's happening. Like they said, the third piece is that those other considerations. So we're looking at housing and power, communications, maintenance and cost. And all those things should be considered when you are looking at your parameters and site locations, because there's a cost benefit of the ease to use a site and the usefulness of that site. Those don't always play off each other, but they can. And so those are just things to consider. But the last piece of that is where does this data go? So it's not just about citing that monitoring station. It's about understand how you're going to get that data back. So I've got communications on there. Some of the most popular communication means are SCADA, cellular is becoming bigger, but AMI or advanced metering infrastructure, if you've got the right system, can be a really good asset as well. And so then, depending on what communication backhaul you choose, where that data lives, how you can access that data matters as well. So I'm going to go into a little bit more information on that by going through a couple examples. So the first type of kind of parameter we might want to look at, mentioned, was chlorine residual. So what I'm showing here is a chlorine analyzer and a gateway interface. So this is essentially a radio that operates over our AMI system or our smart utility network. And so typically we would place something like this at an existing infrastructure, like I said, a tank or a pump. And the reason we would do that is because the chlorine analyzer is going to require external power, and it's going to require monthly maintenance. And so we want that in locations that we can visit frequently. But in a lot of cases, we want, as a utility, we might want to go and visit that pump station or tank on a monthly basis anyway, just to get our eyes on it for routine checkups. And so it's really not that big a deal to go refill the reagents anyway. I've got on here the smart gateway interface because we want to, in this case, we wanted to look at all of our communication options, and based on where we might want to site this, we'd want to leverage whatever communication network we could at the lowest cost. And so in a lot of cases, if you own the infrastructure, if you own your AMI network, then you can leverage that as well. What that looks like on the data monitoring side is all this data is coming back to the AMI head-end system. And this can be really helpful because now we don't just have monthly grab samples. We now have 5-minute data, or we could tune this to different intervals as well. And so this can be really helpful in calibrating and understanding our system. Maybe we're putting too much chlorine in the system than we really need to be. But the other really important component to consider when thinking about online water quality monitors is the algorithm or what triggers going on to the next step. So what triggers this is out of bounds. And so we need alarms. So we need something to tell us, hey, we've got a problem, we need to investigate further. And so And what we can do is we can look at, we can set threshold alarms that will automatically send a text message or an email to somebody saying, hey, there's an issue. This doesn't necessarily have to be the way it's set up. You may have only one of these in your system and you say, hey, we don't need alarms because we're just going to put this up in the operating room and somebody's going to be looking at it all the time. That's a fine strategy as well. It's just something to consider as you look to include 5, 10, 15 of these in your system. And like I said, pressure and temperature are not always thought of as water quality parameters. But I wanted to bring up this because it's a really good case in which this utility happens to be Walla Walla, Washington. They leveraged AMI to truly create a smart utility network. And what they did is they used some of these residential water meters with integrated pressure and temperature sensors that's shown in the bottom left to get a really good distribution of sensors throughout. And so they were able to do this because, one, it's integrated into the meter, so the difference in cost over a standard residential meter wasn't that much. But then also it's utilizing that communication backbone that they already had. To compare this, if you were going to try to do this using a different communication backhaul, such as cellular, you'd really want to account for all those costs. And so I bring this up because you really want to compare and contrast the pressure and temperature type monitoring with chlorine analyzers or some of the other parameters. And you really have to consider these holistically. The way I kind of like to explain this is it's a bit like an analogy. It's not an either or. It could be a both, or it could just be one. I almost view, if you think about the game chess, and the chlorine analyzer would be very reflective of like a bishop or a rook, whereas a water meter with integrated pressure and temperature, those would be more like pawns. So you could afford a lot more of them. Moving on to the enhanced security section. The whole idea behind enhanced security is to protect those remote assets from attack as well as vandalism. And so I almost like to think of this as the teenage protection. And the EPA recommends there's a couple steps in this, and the first is hardening. And so what they mean is you have to make it hard for somebody to get into those remote assets. And so this could be fences or locks, barbed wire, bollards, whatever just makes it difficult. They don't have it here, but one of the things I've seen some utilities do is that they hide in plain sight. So this really reminds me of secret agent stuff where they make the pump station look like any other house. The next component is the intrusion detection. And so this could manifest itself in a lot of different ways. It's going to depend on the criticality of that asset. This could include CCTV, motion sensors, door alarms. And so that's just something that you're, again, going to have to weigh the cost benefit of, do I really need the highest level security here, or can I get away with something cheaper, and what makes the most sense? And then the sites they recommend are obviously things that intruders could get into, so like pump stations or tanks. But these could also be like PRV vaults. So looking at one example of that is utilizing door switches. So that can be a really cost-effective way to monitor the comings and goings of anyone into a particular building. And so the way this works is you've got a magnetic reed switch, and this isn't this is exactly like really what you might have in your home security system with the windows. And so you've got two magnets, and when that magnet trips, when the window's open, triggers alarm. And so in this case, we can hook that digital reed switch to a smart gateway interface and get that data back over the customer's AMI system. The benefit of doing it this way is that it's near real time. You don't even have to necessarily wait for the next polling because the magnetic read switch is continuously being pulled. And you can get these text and email alerts. So within just a minute of somebody opening a door that you want to know about, you could get a text message saying, hey, there's something going on there. And of course, like I mentioned, it's very cost effective. Moving on to meter tampering and backflow alarms. The idea behind this is that there's a lot of data coming from these meters that, one, tell us about the meter health, but they can also inform on system problems. And a couple that the EPA has really honed in on are tampering alarms. So tampering alarms could represent somebody maliciously attacking the system because a tampering alarm is triggered when the meter, as it says, is tampered with. So somebody's maybe trying to remove it from the ground, and that makes it an accessible point for anyone who wants to get something into the distribution system. All they have to do now is overcome system pressure. Backflow could be another example of this, where somebody could be trying to overcome system pressure from inside the residence or inside the building. And so you'd get a backflow alert. Backflows could also be manifested, especially in the case where utilities don't have backflow devices. This could be representative of a break. So if there's a break down the hill from customers that are all showing backflow alarms, that could just mean that the water from inside their houses are running down the hill because there's a break and they're just going down the hydraulic grade line. The one thing I wanted to talk about here is the presence of on-node alarms and how they reduce response times. So when I say on-node alarms, I'm essentially saying there's a firmware alarm on the meter itself saying, detecting whether or not there's tampering or backflow or otherwise other alarms. This is different from like a software alarm. Both are useful, but software alarms would be just the raw data is going back to the head-end system, and then a software alarm is deciding whether or not some threshold has been violated. When we're talking about AMI systems and where we are when we're talking about meter alarms, this is important to think about because the way at least our system works is meter reads are recorded every hour and then sent every 4 hours in general. But if the smart point goes to read the meter and there is an alarm, it's going to send it right away. So rather than waiting 4 hours, you get it in an hour. So 4 times quicker response time. And so depending on the system you have to start thinking about what does this mean for our response time? And so having those on-node alarms can really reduce that. The last thing I wanted to mention here is that actually in the figure down below, I'm showing high temperature and low pressure, which are not tampering alarms and they're not backflow alarms. But I bring this up because smart meters, like I was mentioning before, can have more alarms than your traditional meters. So even going beyond tampering and backflow. So they've got additional sensors like temperature and pressure. Those can be additional meter alarms. And talking with one of my coworkers, this is really blending the division between those two, metering alarms and online water quality monitoring. They're really becoming one. But that's really not the point to concretely say which bucket each belongs to. More the point is utilizing the data that you might have access to. Going on to customer complaint. So customer complaints are really important because they represent another source of water quality information. And I'm sure a lot of utilities out there on this call even are already utilizing customer complaints to solve water quality issues. But the EPA, they go into a good bit of detail about what's the best way to deal with this. And so they give some guidance here. And the main construct is, first what we want to do is we want to funnel all of the customer complaints, or really it's customer interactions, because these could be coming not just from phone calls, but they could also be from emails or tweets or whatever the latest platform that teams are using. And then the important part there is get them all into one centralized place, and where customer service can take that information and put them into work orders or have a plan to do something with them. The next step is filter. And so this is really sorting the quality concerns that come from customer service to either, this is a bill issue or this is actually something that ties into water quality, whether that's a low pressure issue or if it's a taste and odor issue. And then focus. Focus is where you're looking not only at that customer information, and so maybe you're looking at the spatial and temporal distribution of these customer complaints, but then looking at other data sources as well. And this is where having some of the online visibility that I've been speaking to, like AMI and pressure, can help quickly sort out a lot of those issues that are not water quality related. So say, for instance, somebody calls in and they say, I've got low water quality at my house, or low water pressure at my house. Can you send somebody out there? Well, now the customer service representative, if they have online pressure monitoring, they can quickly pull up the pressure monitoring application and be able to diagnose, is this something that we need to send somebody out to check on or not? And so this will not only improve response times to issues, but can also improve the customer service by being a little bit more proactive and having that data available. And I think the key here is that we need to have thresholds, those temporal and spatial thresholds to kick it up to the next level of response. And this is where the EPA has also said, this is the lowest hanging fruit. People, or your customers, they are distributed through your entire system. And so they're essentially little monitors themselves. And so it'd be silly not to utilize that. And so this is really the lowest hanging fruit. Moving on to public health surveillance. So in the movies, the spies, they never really want to go to the hospitals. But as agents of public health, we can look to the hospitals for valuable information. And so what I see this public health surveillance or public health monitoring, this is really not so much monitoring ourselves, but it's a partnership with the local health agencies. And so some of the data sources the EPA says are valuable in this case are the poison control call centers, the emergency rooms, and the EMS. But one thing they note is that it's not generally the utilities that are doing the monitoring themselves. It's usually the public health agencies. This is much more case-based, or this can manifest itself in kind of two ways, or both. The first is case-based, and so this is where either doctors or pharmacists, they start noticing trends of their own patients, and they say, this is something we need to look into. And so they need to have somebody to call and say, hey, whoever at the water utility, and say, hey, we think there might be something going on. This is the evidence. I kind of call that the bottom-up approach. It's more acute because obviously those doctors and those health professionals are directly in contact with the people who are sick. But there's another approach, which is more the top-down approach. EPA calls it the syndromic. And this is broader. And so this is really looking at all of the data coming through those different systems and taking more of a data science approach or an epidemiological approach. And then they have to have thresholds on what necessarily triggers a call to the water utility to say, hey, there's an issue. The reason why the EPA includes this, even though it's not necessarily the utility doing that monitoring, is that education goes both ways. So for one, as the people in the public health services or those public health agencies, they need to understand your system just as well as you need to understand theirs. And it's really that communication and relationship with those agencies that is going to be crucial in times of emergency. I mentioned education goes both ways, and I mean that especially from our perspective. We can always learn more about how the water can impact public health, but then they can learn more about where our service boundaries are. So if they know, they may not be aware that your utility not only serves that city, but also the surrounding county. That may just not be within their understanding. So being able to sort those two things early is always helpful. We're going to do another poll here. Now that I've been through the components of the surveillance system, do you have any of these already? So feel free to select all that apply, and I'll give you all a few seconds to answer. All right. Oh, I'm going to guess that a lot of you have more than that, but that's okay. So let's move on to a quick activity. I really want you to imagine that you get a call that the water tower has been poisoned with arsenic. What do you do? And I really want you to think deeply. Do you have a plan for that? So the reason I bring this up is because in the spy movies, the protagonists, they never have plans. They just kind of shoot from the hip, and they always seem to make it out alive and save the day. But this isn't the movies, and we do need plans. I really relate this a lot to if you've ever taken a CPR class, you know, if you're the one that's kind of controlling the situation, the instructors say, you don't just say, somebody call 911. You pick somebody specifically out of the crowd who's maybe onlooking, even if you don't know them, and tell them, hey, you in the pink shirt, you need to call 911. So you need to reduce the uncertainty. And so I bring up this just kind of thought experiment. What do you do if you get a call that the water tower's been poisoned? Because although this isn't a highly likely scenario, I'm sure you all deal with situations like, hey, there's a main burst on Main Street. What do? We need to have a response plan for the entire gambit. So I'll go a little bit into the response side of things. And really, this is a timely conversation because the America Water Infrastructure Act, or AWIA, it requires kind of a high-level emergency response plan. And if you actually look at the EPA's guidance, a subcomponent of that can include a contamination response plan. And at the end of the day, this really just comes up with, if we do have a problem like I showed on the previous slide, if we do get that call or that data shows something, we have a plan. And the first piece of that is investigation. So if we do have a problem, we're going to go check the other data sources. So if we see something strange on our chlorine analyzer, are we going back to check, hey, is the pressure in that area all the same? We might be following this up with some hydraulic modeling, whether or not you're doing that in-house or you're calling up your consultant to do it. And then the response component of this is, what are we doing to mitigate the challenges? So are there operational changes? Are you going to start running your pumps more or turning over the tank? Of course, a lot of this depends on what kind of problem you suspect it is. There could be isolation, so shutting valves in order to isolate the problem, prevent the contamination event from getting from one pressure zone into another. There might be use restrictions in order to protect people, and really a key here is how you respond in communication, both internally and externally. Final component here is that remediation and recovery. And this goes into the problem characterization. And so really understanding, okay, fundamentally, what is the problem? So we should have already gone through the investigation and we're already responding, but now we have a really good sense of what the problem is and we know how to fix it. And that brings on the decontamination phase. So implementing that plan to decontaminate whether that's coordinating just internally or if you need to bring in other external partners as well. And then having that threshold saying, okay, this is what we need to get our system back to in order to say the contamination is passed, we're cleared to go. I won't go into all the bits on that, but I will hit a couple key parts. On the sample and analysis component, this is an important part that is investigating the possible contamination. It's a plan that needs to be enacted so that way if you do have a suspected contamination event, you know how to respond and how to collect those samples. And so it starts with the visual site hazard assessment. One of the things, especially if you're thinking it could be a malicious attack, you have to make sure your staff have a good sense of what they need to do. And so they need to be safe. They need to first survey the area in order to make sure that it's safe for them to approach that pump station or tank. This may involve having the local law enforcement there with you too. Once you get on site, you need to go into the sample collection mechanisms, in-field parameter testing, and then packaging up that sample. They throw in-field parameter testing. That may not be applicable for every case and every utility, but having devices that you can easily test parameters out in the field can really speed up things, but that's not always going to be possible. And then there's some things that there just aren't those type of analysis methods in the field base yet. So that's where the laboratory analysis comes in. Moving on to the consequence management, this goes into minimizing the impacts of the contamination. There are a couple things that we can do. I mentioned we can isolate, we can flush, we can change our operations. But I think it's really important to consider that if we're talking about our hydrants and our valves, these are really distributed assets that a lot of times get neglected. I was reading that it's about 40% of the valves in the US are not operating properly. 15% can't be located, 10% buried or paved over, 9% in the wrong position, and 6% broken. So this is really important to consider if you are going to rely on your valves to mitigate contamination events. And then you also have to consider that usage restrictions impact hydraulics. And so you may have a really good understanding of your hydraulics during normal conditions, but if you've already issued use restrictions, you have to take that into account. And so if you really want to nerd out, there's a good paper linked down at the bottom that really talks about how during a contamination event, those usage restrictions can impact hydraulics and impact flushing. So let's do one more poll. What components do you feel like you're ready to adopt? And this again, select all that apply. So apparently I clicked a little too fast through the last one, so I'll give you a few more seconds on this one. Here we go. Let's see. Excellent. That's exactly what I was hoping to see. The response plan is the number one thing you're wanting to adapt. I really feel like that is the most important. As we all know, data for data's sake is pretty meaningless if you don't have a plan. So kind of to summarize, we've looked at the surveillance and the response side. There's monitoring a lot of different data parameters. We're either automating where we can to decide whether or not there is a problem, and then having a plan afterwards. But before I wrap up, I wanted to bring up one more thing. And that's a really interesting article I recently read in the Journal of American Waterworks Association. And that's essentially the thesis of the article was that utilities are facing more litigation costs due to water quality lawsuits than ever before. Essentially what's happening is the courts are requiring more due diligence on the defense side when a water quality lawsuit is levied. And this has only become a more recent thing because historically utilities were more protected by the immunity defenses. But that isn't necessarily the case anymore. The good news is, and I really appreciate this quote, is towards the end of the article, they said municipalities and water utilities can win these fights before they even begin by doing the right thing in the first place. A defendant who can show in court early on why its actions were justified or even noble will stand a much better chance at winning an immunity argument and winning it sooner. Essentially, if we are taking the proper precautions, we're showing good faith, we're doing our jobs well, and we've got data to back it up, we're following EPA's best frameworks, we're going to be able to avoid costly litigation, even if in the end we were going to be found innocent or the case would be thrown out regardless. So in conclusion, implementing a surveillance and response system can really bring us the peace of mind knowing that there is a problem, we will be ready. If there's 3 takeaways I hope you take away, have a response plan to contamination events, implement the most accessible surveillance first, and being proactive protects human health, improves operation, and can limit risk. And the way I like to think about it, if we do these things, we can be ready for whatever is thrown at us, and we can be calm, cool, and collected, just like the spies in the movies. With that, here's the link to EPA's water quality surveillance website. Some really great resources there, and I believe we've got a few minutes for questions.
Thank you so much, Zach. Zach's right. At this time, we'll move into the question and answer portion of the program. And we have a few minutes, but if you would still like to ask a question, you can do so by clicking on the purple Q&A icon in your engagement toolbar. So the first one we have here, what response timescales would be required for responding?
Yeah, I think that's a good question. It's going to depend a lot on the type of contamination and the type of event. Usually the bottom line is just the quicker you can respond, the better. Minutes count, but it's going to depend a lot. And so going through some of the questionnaires the EPA has out on their website on how to kind of evaluate your own systems has some really good resources there. Thanks.
Okay, and the next one, could artificial intelligence aid in the monitoring and event detection that you talked about?
Yeah, that's a really good one. And that's a field that's going to, I think, really evolve over the next few years for the water industry. It started to show some promise. And one of the things that excites me most is I was mentioning those different surveillance monitoring data streams. A lot of times we are just analyzing one of them at a time, but AI is starting to look at those different parameters together. So yeah, I think that's going to be really exciting in the future.
Awesome. Let's see here. In the pressure monitoring example that you gave, what sort of sensor density is required?
Yes, sensor density, always a good question. I was actually at a webinar last week during the AWWA Summit where that exact question was posed, and the responses I think I'm going to steal from them, from Tom Walsky. He said there really isn't a good number of sensors, it's a continuum. The more sensors are always better, but there's a trade-off in cost. And so being able to leverage cheaper sensors, or more, not cheaper, but more cost-effective is probably the right word for that. Cost-effective sensors to get a good blanket over a distribution system is usually the way to go.
All right. How often should surveillance and response systems be updated, in your opinion?
So I would say that's something that should be continually done. The EPA may give some guidance on that. I'm not familiar there, but having that yearly review, I know I've heard a lot about the emergency response plans that WEA requires. I think those are a 5-year review, but I think the best practice would be a yearly review.
Okay. Let's see. How can consumption data be used in surveillance and response systems?
Oh, good. I'm glad I got that question. So I think this stems from with AMI data, with AMI and with smart metering systems. Now we've got more consumption data than we ever had before. And so this can play into a couple ways. One is now we can start to understand what the demand is on a really granular level and how different things impact that demand, like weather, for your own utility and not just using engineering judgments that are conglomerations over a lot of national data. But I think where this is going is kind of that idea of the digital twin. And so this data could be very valuable in driving real-time decision tools that are essentially telling you how the hydraulics in your system are working. Because as we all know, hydraulic models are only as accurate as the data supplied. And a lot of times we have to make assumptions for the demand curves. And so we can remove one of those assumptions here.
All right, and I think we've got time for one more question. So let's see, what asset types are most security critical in a water system?
Yes. I'm going to hedge my bets a little bit here because I think it's going to depend a lot on the utility themselves. But tanks and pump stations represent really critical assets. One, because of their exposure, they're more exposed than other assets, so they represent a higher likelihood of getting into them. But they also have more moving parts, especially when you're talking about pump stations. And so things can fail on their own. And this is why I think a lot of utilities have already invested in monitoring pump stations in order to keep a good eye on them. And this is a trend that I think will continue.
Oh, great, thank you. So on behalf of WaterWorld and Endeavor Business Media, I would like to thank today's speaker, Zachary Barkjohn, as well as our sponsor, Sensus, a Xylem brand. I'd like to remind everybody that any unanswered questions will be forwarded to the presenters to answer offline. And today's presentation, Building Your Water Quality Surveillance and Response System, will be archived within 24 hours and can be accessed at waterworld.com for the next 6 months. A reminder email message will be sent to all registrants with a direct link to the archive. One final note is that a certificate of attendance for today's webcast will be sent out to all registrants, and you may also download it now by clicking on the yellow certificate icon if you wish. We thank you for joining us today and look forward to serving you with future webcasts. This concludes today's presentation.